Hi, my name is Amanda Singleton. This summer I've been working with Mike Garcia in Sumita Penniker's lab, separating particles using tangential flow filtration and inertial microfluidics. So in the medical field, it is often very important to be able to separate cells. For example, counting white blood cells is important in diagnosing diseases. And microfluidics offers a way to count cells in a way that is efficient, automatic, and uses a smaller sample size than other methods because of its micro nature. So how does microfluidics accomplish this? Here's some background. Reynolds number is characteristic of fluid flow. With very small Reynolds numbers, we get viscosity as the dominating force. For very large Reynolds numbers, inertial forces are dominant. We're really interested in the regime where these two forces are balanced, between Reynolds numbers of 1 and 100. In this regime, we get inertial focusing. Inertial focusing is what happens when you start with a random distribution of particles and they focus as they get ran across the channel, as seen in the diagram on the right. And in a square channel, we get 4 equilibrium positions. The diagram on the left shows a top-down view of the one on the right, where these 2 equilibrium positions are the same as these 2. Inertial focusing happens as a result of 2 main forces. The first arises from the difference in velocity. When a fluid moves through a channel, the velocity is highest in the middle and slowest towards the wall. This difference causes the particle to be pushed towards the center of the channel, towards the wall of the channel. And then the force that forces it towards the center of the channel arises from wall interactions. This happens when the particle flows through, creates a wake, and the wake bounces on the wall and hits the particle, pushing it towards the center again. Currently in microfluidics, it uses inertial focusing and inertial microfluidics to separate particles. This works and it's cool, but it has limitations. Currently, the microfluidic devices need to be fabricated specifically for certain known cell sizes. And if you want to separate cells that are, say, of different sizes, you have to fabricate an entirely new chip. This leads to inefficiencies in time as well as production costs. So we're adding tangential flow filtration to our main channel. This still has the same idea of inertial microfluidics, but we're adding the idea of permeate channels that run off to the side. These are the smaller channels that are perpendicular to the main channel. This allows us to add a permeate flow, which allows us to vary the flow in a way that the straight channel does not. When the flow rate in is larger than the flow rate out, that's what we define as the permeate, and it shoots off in these 2 directions. Whereas the straight channel, the only thing that you can vary is the flow rate in. With the TFF, you can vary both the flow rate in and the flow rate out because the permeate makes up the difference between the 2. So I'm interested in figuring out how varying the permeate affects where the equilibrium positions are, and what this effect, and how this effect is dependent on particle size. So, I'm looking at the end of the permeate channels, and I'm using fluorescence microscopy to take long exposure images of my particles. This gives me a look at the probability of the particle's location. So the white streaks that you see are where the particles are most dense, the particle equilibriums. We also use the long exposure technique to show an accumulation of many particles to get a better nature of that fluid flow instead of just tracking one particle. So what I'm measuring is the distance between the center of the channel and one of the particle equilibriums. I do this by taking half the distance between the peak to peak because the 2 peaks are symmetric about the channel center. A qualitative representation looks like this. I'm looking at varying the flow rates, and I can see that it changes the x-equilibrium position. Now, because it's symmetric, I only care about the top half, because it's redundant information. And if I want to look at this quantitatively, it looks like this. So here's my day. I'm looking at a solution that has both 15 and 5 micron particles. And we can see the same trend that we saw in the qualitative data, where as the ratio of flow rate out to flow rate in increases, we see a decrease in the x-equilibrium. But we see that the 15 and 5 behave differently. We think that the smaller particles, the 5 micron particles, are more influenced by the change in flow rate because they have less inertia because of their smaller mass, whereas the larger particles have more inertia and are harder to move around for the same given flow rate. What we're interested in is the difference between them. This is a physical difference in the equilibrium location that allows us, or that should allow us in the future, to separate the particles. This particular graph is only for a flow rate in of 50 milliliters per hour. We want to vary that to see what else happens. So if I take this difference between the 5 and 15 and plot that for different flow rates, I get this. So each color represents a different flow rate in, and the height of each marker represents the difference in 5 and 15, the physical difference. So with the exception of the 10 milliliters per hour, we see that the trend sort of goes like this, where the dip in the middle is where they cross over and don't have any separation in between. And we also see, pretty cool, that at 0.2 and around 0.9, we see the separation is maximum. This is the sort of parameters that we're looking for to be able to separate particles most easily. And we can conclude that indeed changing the flow rate changes the different sizes of particles in a different way from one another. Additionally, we would like to explore how this x-equilibrium changes as a function of channel length or channel location. And we think this happens because of something called permeate recirculation, which is when fluid enters the permeate channel, or permeate was, and then recirculates back into the main channel, increasing the velocity then at the end. And this was an unexpected addition to our chip that we hadn't expected. So we would like to figure out a device where there is actually a constant permeate flow and see how the interactions between particles and the flow happen when that is actually constant. And then after we do that, we would like to verify that we can actually separate the particles like we should be able to using this method. I would like to thank CSEP, CNSI, ICB, and the Gorman Scholars Program for making this project possible. Thank you. Any questions? Yes?
Is there any way of theoretically just on paper trying to solve for equilibrium position?
Yeah, so this project that I presented is my undergraduate work, but my mentor, Mike Garcia, is actually working with COMSOL to try to figure out and run pretty much the same experiments, but exactly what you just said, trying to be able to predict the equilibrium positions. Because actually in literature, that's something no one's been able to do, is given a set of parameters, predict where they are, except for experimentally. So we're trying to also see theoretically using numerical simulations. Yes?
So I think that you did a very good job. What is, I guess in real life application, what would be the sizes and range that you're using the 5 and 15?
Right, okay. Yeah, so a red blood cell is between 6 and 8 microns, and a white blood cell is between 12 and 15. So we're working, I collected data for 5, 10, and 15, which is around the same size as red and white blood cells. Yes?
Have you done experiments with two particle sizes at the same time?
Yes, the 5 and 15 are at the same time.
Okay.
I've also done them separately. If you come on Thursday, you can see my poster, and it has more data represented.
Okay.
But the 5 and 15 are, I was pretty excited about the graph that shows them crossing, because I'm using fluorescence microscopy, but the 5 and 15 are tagged differently, so I can change the filter on the camera and actually see differences in between them, because I've also tried 15 and 10 together, and they overlapped because they had the same tag. But yeah, so the 15 and 5 are in the same solution together.
Okay, and they behave the same way, depending on whether they're by themselves or together?
They behave very similarly, yeah. Yes?
Okay, so this is a two-part question. The first part is, I understand that you're modeling this with some laboratory sample like beads or something like that.
Yes,
to
we're
measure
using
the
polystyrene
blood.
beads.
Okay. If the application is for red or white blood cells, do you think that there's going to be a complication in actually monitoring the cells if the cells are basically like damaged through this process, or has that work been done to see if you can even like flow a giant white cell, like white blood cell particle through?
So the current inertial microfluidics has the same sort of dimensions as we do, and like micro. So I imagine what they've been doing with blood and samples has already worked, and the only thing that we're doing differently is adding the permeate channels.
Okay. And so the second question, I'll have to get back to you, I lost it.
Okay. Yes?
Are there any limitations in the viscosity or the density of the solution that you can be flowing through, given that your permeation channels are really pretty small?
Yeah. This is true of all microfluidics, not just the permeate, but this clogs a lot. Like a lot. And I mean, you just gotta work with that. Yeah. It's micro, and you have, it just clogs with like fibers from your clothes, and then you gotta flush it out with water. And yeah. So.
But that's not a concern with the types of real life samples you might want to be running through it.
Like no more so than other current microfluidics that are being used. It's pretty much a problem for all of us.
Okay, how wide are the channels again?
Oh, right. The channels that we're working with, the square channel is 100 microns by 100 microns, which is also the width of a human arm. And the chip itself is about 3 centimeters across.
And so the cost for manufacturing one of these is how much?
I'm not entirely certain. We're pretty simple ingredients. It's a silicon wafer and borosilicate, so glass, bound together. Etching might be where the cost comes from. It also takes about 6 days for fabricating a new chip. I'm not sure exactly the price on it though.
All right, thank you, Amanda.